Greetings of the day. I am Dr. K. Raghuram Mohan Reddy. The course name is Unconventional Machining Process. Today's topic is EDM with ultrasonic assistance. Okay, I'm the professor of Mechanical Engineering Department. Right. At the end of this session, students will be able to understand the working of EDM with ultrasonic assistance. Okay, this is the course learning outcome. Now let us see the different categories of non-conventional machining process. So under non-conventional machining process, basically there are three categories: mechanical, thermal, chemical and electrochemical. Under mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. Under chemical and electrochemical, chemical milling, plasma chemical milling, electrical chemical milling. Under thermal, electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. Now we are under electro discharge machining. Okay, right. Now let us discuss electro discharge machining with ultrasonic assistance. The need for machining hard and brittle material is steadily increasing in many applications. Okay, right. The applications of EDM with ultrasonic assistance is in many applications because there is a huge requirement for hard and brittle material machining. For this, EDM with ultrasonic assistance is very much suitable. Traditional machining as well as some of the non-conventional machining process present several problems related to tool life and produced surface cracks. Okay, with some traditional machining process, we have some problems. Okay, those are tool life and surface cracks. Okay, so here tool life and surface cracks are predominant parameters of the machining. Here we have to have a good tool life and there should not be any surface cracks after the machining. So for this, EDM with ultrasonic assistance is best suited one. In place of traditional and non-conventional machining process, EDM with ultrasonic assistance is best suited for hard and brittle materials and have more tool life and good surface finish without surface cracks. Right. EDM can be applied to conductive hard and brittle material of electrical resistivity below 100 ohm centimeters. Okay, right. A major drawback of the process is low efficiency of sparking and formation of open circuit, arc, short circuit pulses, which are non-productive with respect to material removal rate. Okay, let me reiterate. EDM can be applied to conductive hard and brittle material of electrical resistivity below 100 ohm centimeters. And regarding drawbacks, a major drawback of the process is the low efficiency of the sparking. and the formation of open circuit, arc, short circuit pulses, which are non-productive with respect to the material removal rate. Right. Ultrasonic machining can tackle hard and brittle materials which have difficulty withstanding the cutting forces during conventional machining. Already we have come across with conventional or traditional machining process. There, the machining of hard and brittle materials is very tedious and very difficult one. But here, with ultrasonic machining, hard and brittle materials can be easily machined without any surface cracks. Okay, good surface finish will be obtained. Right. At low machining rates, parts having a good surface finish can be produced using ultrasonic machining. Okay, so here at low machining rates, parts having a good surface finish can be produced using ultrasonic machining. Right. Now let us see this EDMS schematic. Okay, right. The interaction between machining mechanisms of electro-discharge machining and UAS, that is ultrasonic vibration, in one machining process, that is EDMUS, okay, has a greater productivity than the sum of the productivities of the individual EDM and USM at the same machining conditions. Okay, so by individual, EDM and USM have some features, some advantages, but combinedly we have a greater productivity than the sum of the productivities of the individual EDM and USM at the same machining conditions. Okay, this is the setup or schematic of ED and US. Okay, electro discharge machining ultrasonic schematic. Okay, right. Right, this is the schematic of EDMUS. See here, DC power supply. Okay, positive terminal is connected to, excuse me. See here, DC power supply is using positive terminal is connected to workpiece and the negative terminal is connected to tool. Okay, again, however, the tool is connected to horn and the horn is extended for the ultrasonic vibration setup, leads to transducer winding, and here dielectric fluid is supplied to the workpiece and the tool. Okay, however, the spark generates between tool and the workpiece. This is the schematic EDM US. Okay, right here, electro discharge machining and ultrasonic vibration setup is combined so that we'll have the advantage of both EDM and US, that is ultrasonic. Right, right. The new process is adapted for rapid production of graphite electrodes for EDM, where cutting, drilling, and engraving can be done easily. Okay, what are the operations? Cutting, drilling, and engraving can be done easily with this new process, that is EDM with US. Right, the machining components and the systems have seen in the figure EDMUS. Okay, it is similar to that of USM with dielectric replacing the abrasive slurry as the machining medium. Okay, right. The ultrasonic vibration of the tool or workpiece together with the low cost DC power supply generates the discharges across the machining gap. Okay, right. Here the components of EDMUS. Right. Here EDMUS is the main mechanism to remove the material removal. Okay. The material removal mechanism employs the electro discharge phase for melting and evaporation of the workpiece material by the plasma channel in a similar way to normal EDM as shown in this figure. Okay, in EDMS, EDM electro discharge machining, under that EDE phase, electro discharge evaporation phase, okay, with the combination of plasma. Okay, so here for tool we are setting the ultrasonic vibration. Okay, ultrasonic vibration that we have attached to the tool already equipped with the electro discharge machine. Okay, however, the dielectric fluid medium is flowing or circulating between the tool and the workpiece, okay, where the spark generates. Okay, so this is the component of EDUMS, electro discharge machining ultrasonic. Okay, right. The intensity of the discharging action depends on the working conditions such as gap voltage, amplitude, and frequency of ultrasonic vibration, as well as the gap flushing conditions. Because of the ultrasonic vibrations of the tool, its front surface move down toward the workpiece surface and the electric field intensity increases. Okay, the intensity of the discharging action depends on the working conditions such as gap voltage, amplitude, and frequency of ultrasonic vibration, as well as the gap flushing conditions. Because of the ultrasonic vibrations of the tool, its front surface move downward, the workpiece surface, and the electric field intensity increases. Okay, right. The electric field, however, causes the ultrafine particles, that is, metal debris ejected from the formed crates in the machining medium to be suspended and form a bridge across the gap. Okay, so about electric field, the electric field, however, causes the ultrafine particles in the machining medium to be suspended and form a bridge across the gap. Okay, what we have seen in the figure. Right. Working. At a very small gap size, deionization or breakdown of the working fluid occurs and the plasma channel is formed. Okay, see here, at a very small gap size, deionization or breakdown of the working fluid occurs and the plasma channel is formed. Okay, at very small gap size. Okay, now on the other hand, we'll see at very large gap sizes. Okay, when the tool front moves up, the gap voltage raises, current drops, and the plasma channel collapses at large gap sizes. Okay, right. The process begins again when the tool moves down. Okay, so when the tool moves up and the tool moves down. Okay, right. When the tool front moves up, the gap voltage rises, current drops, and the plasma channel collapses at very large gap sizes. Okay, right. The process begins again when the tool moves down. Okay, right. Here again, just look at this very small gap size. Deionization or breakdown of the working fluid occurs and the plasma channel is formed. Okay, right. See, look at here. It will have to go up and down, and the gap size will increase and decrease. Okay, so when the gap size is very small, that means when it comes down. Okay, when it goes up, the gap size will be increasing. That means at large gap size. Okay, that is when moves up. Okay, right. Ultrasonic vibrations as a gap flushing method in the mechanical pulse electrode discharge machine, that is MPEDM. Okay, mechanical pulse electrode discharge machine. Okay, EDM means electrode discharge machining. So far we have studied. Okay, proceed to this EDM MP, that is nothing but mechanical pulse. Okay, ultrasonic vibrations as a gap flushing method in mechanical pulse electrode discharge machining. Cavitation bubbles and the ultrasonic field force prevent the sedimentation of the debris particles in the working fluid. Okay, what does it mean? Cavitation bubbles and the ultrasonic field force prevent the sedimentation of the debris particles in the working fluid. Okay, right. Right. Pumping action. The high frequency pumping action improves the working fluid circulation by pushing the debris away from sucking fresh fluid into the machining gap. Okay, see here, usually we have gap between the tool and the workpiece. That is nothing but machining gap. Okay, so because of this high frequency pumping action, it improves the working fluid circulation by pushing the debris away and sucking fresh fluid into the machining gap. Okay, that is because of high frequency pumping action. Okay, right. These stoutly increase the discharge efficiency and give higher erosion rates. Why? Because the debris will flush away and it constantly sucks the fresh fluid into the machining gap. So that's why it increases the discharge efficiency and give higher erosion rates. Right. The flushing action has been reported to increase with vibration altitudes. Okay. So here the flushing action will increase with vibration amplitudes. Okay. Right. However, we have to manage both ultrasonic and electro discharge machining parameters combinedly in order to have both the advantages of EDM and ultrasonic machining. Right. Regarding tool wear rate and sparking efficiency. Right. Let us see here. With the application of ultrasonic vibration, the machining rate and surface finish improved significantly. Okay. The application of ultrasonic vibration, the machining rate and the surface finish improved significantly, and although the tool wear rate increased, the wear ratio was not influenced significantly. Okay, so here the tool wear rate has increased because of the ultrasonic machining and vibration and the electro discharge machine. Right. Here, some other scientist named UD reported that the increase of tool vibration up to 100 microns enhanced the erosion rate due to the improved flushing action and hence the sparking efficiency. Okay, UD during 1995 reported that the increase of tool vibration up to 100 microns enhanced the erosion rate due to improved flushing action and hence the sparking efficiency. Okay, so here the sparking efficiency will be improving because of this flushing action. Okay, and the vibration of the tool. Right, right. Regarding debris, so let us see the debris influence on the material removal rate. The presence of too much debris in the electrode gap causes continued arcing and short circuits, which makes the process unstable. Okay, so because of this debris, what is happening? Too much debris in the electrode gap causes continued arcing and short circuits, which makes the process unstable. Okay, there should not be continuous arcing and short circuits. Okay, right. The dielectric must therefore contain an appropriate amount of debris, since a medium that is too clean is another reason for gap short circuiting and the consequent machining troubles. Already we have discussed. Okay, so here the dielectric must therefore contain an appropriate amount of debris only. Okay, the debris is too much, then what will happen? Continued arcing and short circuits. Okay, subsequently the process will be unstable. Okay, so there must be only a small amount of debris can be allowable. Okay, during the machining. Okay, so that will be referred by Machua and al. During 1992. Okay, right. Right. Next, regarding contamination level. The breakdown distance of the electric field is greatly influenced by the contamination level of the machining medium. Okay, the breakdown distance of the electric field is greatly influenced by the contamination level of the machining medium. Okay, so here dielectric medium must not have too much contamination. Okay, right. The gap distance therefore changes from one place to another according to the local contamination level. Okay, so because of this contaminations, what will happen? The gap distance changes from one place to another. Okay, such a change causes dimensional errors in the copying process. Okay, so because of the debris, the dielectric fluid medium will be contaminated. Okay, this contaminated level increases, then definitely there will be trouble, and therefore changes from one place to another. Okay, the gap distance therefore changes from one place to another. Okay, right. Right, regarding the electric field concentration, if the electric field concentration is made uniform anywhere in the inter-electrode gap, the machining gap becomes uniform and an accurate copy is ensured. Okay, the electrode field concentration is made uniform anywhere in the inter-electrode gap, the machining gap becomes uniform and accurate copies ensured. Okay, so if this one is uniform and this machining gap becomes uniform. Okay, the electric field concentration is uniform, then definitely the machining gap becomes uniform. Okay, right. Look at this. Electric field concentration is uniform. Then the machining gap comes uniform. Okay, right. Right. Now let us focus on ideal flushing. Ideal flushing must therefore maintain a constant and uniform debris concentration. So here we cannot completely avoid the debris in the dielectric fluid medium. Okay, so a constant and uniform debris concentration will give good results. In this regard, jet flushing with nozzles sweeping along the inter-electrode gap has been introduced by Mazuzwa et al. During 1992 and proved to be effective in precision EDM. Okay, so here uniform debris concentration is the important one. Okay, constant and uniform debris concentration. Okay, right. Right. Next, the gap contamination. Schumacher during 1990 concluded that the gap contamination through eroded debris influences ignition delay as well as the discharge location in the gap. Okay, ignition delay as well as the discharge location in the gap. Already we have discussed that there will be an arc generated between the tool and the workpiece. Okay, right. This is tool. This is workpiece. This is arc workpiece. This is tool. So here, what we are saying that the gap contamination through eroded debris influences the ignition delay as well as the discharge location in the gap. Okay, this gap, the discharge location, the gap. Okay, right. influence of other parameters, let us see. Okay, the various other researchers have discussed the way backs during 1975 recommended a dielectric flow velocity of 6 meters per second, which reduced the electrode wear by a factor of 2 and the surface roughness by up to 50%, increased the machining rate and reduced the thermal effects in the eroded workpiece surface. Okay, so here dielectric flow velocity is 6 meters per second, that it has been recommended by Wells and Wiley during 1975, which reduced the electrode wear by a factor of 2 and the surface roughness by up to 50%. Okay, right. So these are the other parameters in place. Now let us see the comparisons between EDM, USM and EDMES. Okay, EDM means electro discharge machining, USM ultrasonic machining. This is the combined or combination of EDM and USM. Okay, we'll get the combined effect of EDM and USM, that is EDMES. Now here three: USM, EDM and EDMES. Okay, we have four workpiece materials. Okay, SG4 SiC, SG4 again ceramic. Okay, and SiC in the two materials only. Okay, two materials SG4 and SiC under the different categories like material removal rate and the surface roughness area. Okay, right. So here material removal rate for these two materials for the ultrasonic machining 1.81 and 1.95. Okay, and for EDM this is 2.68, for SiC it is 2.5, and for EDMUS 5.15, and for SiC it is 4.9. Okay, when come back to surface roughness for three categories USM, EDM and EDMUS. Okay, for SG4 0.93 and for SiC it is 0.95, and for EDM 7.9, this is 6.8, for EDMUS this is 2.34 and this is 2.36. See, however, here material removal rate for this or this, it is raising from USM to EDM, again from EDM to EDMUS. Okay, raising, again rising regarding the material removal. Okay, but regarding surface roughness, what is happening here? Here, whatever it may be, whether it is SG4 ceramic or SiC, for ultrasonic machining, the surface roughness is below 1, and for EDM, it is very high 7.9, and again for EDM, yes, it is 2.34. Okay, so surface roughness is very high for the EDM. Okay, right. Right. So the source for this table is Jixin et al. During the year 1995. Okay, so this is the comparison table for EDM, USM and EDMUS for different materials for different conditions of USM, EDM, and EDM US. Right. Now let us summarize EDM US. Okay. Maybe uh, beneficial effects. Okay. It can be concluded that the EDMUS material removal rate is about 3 times greater than that of the ultrasonic machining and 2 times greater than that of the conventional EDM. Okay, so here EDMUS material removal rate is 3 times greater than the EDM and 2 times greater than the US. Okay, right. Moreover, the surface roughness of the hybrid process is greatly reduced to one-third of normal EDM by the introduction of US vibration to the tool or workpiece. Okay, so regarding surface roughness of the hybrid process is greatly reduced to one-third of normal EDM by the introduction of US vibration to the tool or workpiece. So that's what we have discussed here. See here, this is 7.9. Okay, one third means 2.34 almost. Okay, that has been reduced to one third. Okay, one third of the normal EDM. Okay, right, right. Beneficial effects. Those are researcher comments. Okay, various researchers have identified or investigated certain beneficial effects regarding surface roughness and the other parameters of the EDMUS. Okay, in particular, surface roughness. Surface roughness produced by normal USM ultrasonic machining is 40% of those machined by EDMUS. Okay, so surface roughness produced by normal USM is 40% of those machined by EDMUS. Okay, next, during 1995, Jackson et al. Reported a significant increase in removal rate with applied voltage and little effect to the vibration amplitude. Okay, is this Jackson et al. Reported a significant increase in removal rate with applied voltage and little effect to the vibration amplitude. Okay, and additionally, the work of Zhang et al. During 1997 and Zhang and co-workers during 2004 showed also that using EDMUS, the material removal rate and the surface roughness both increases with increase in voltage, vibration, amplitude, and discharge current. Okay, so these people have focused on various parameters like voltage, vibration, amplitude, and discharge current. Okay, right. Here using EDMUS, the material removal rate and the surface roughness both increase with the increase in voltage, vibration, amplitude, and discharge current. Okay, so here material removal rate and surface roughness, these two increases with the increase in voltage, vibration, amplitude, and discharge, current, voltage, current, vibration, and amplitude. Okay, so when these parameters increase, the material removal rate and the surface roughness also increase. Okay, once again, material removal rate and surface roughness, these two will increase with increasing current, voltage, vibration, and amplitude. Okay, right. So these are the beneficial effects identified or observed by the different researchers. Okay, right. Now let us conclude with the second beneficial effect of EDMUS concerns the structure modification. Okay, it is very particularly regarding structure modification. Okay, the alternate motion of the vibrating electrode at the ultrasonic frequency creates more turbulence and cavitations that lead to better ejection of the molten metal from the craters. Okay, this in turn enhances the removal rate and reduces the recast material in the machine surface. Okay, so this is the second beneficial effect of EDMUS. Okay, that it concerns the structure modification. Okay, very particular structure modification. The alternate motion of the vibrating electrode, that means this one, okay, at the ultrasonic frequency creates more turbulence and cavitations that lead to better ejection of the molten metal from the craters. Okay, when arc craters develops between the two and the workpiece, definitely there will be a required turbulence, then only it will flush out the entire debris and it will maintain a significant or required debris percentage in the dielectric fluid medium. Okay, okay. The alternate motion of the vibrating electrode at the ultrasonic frequency creates more turbulence and cavitations that lead to better ejection of the molten metal from the craters. Okay, right. This in turn enhances the removal rate and reduces the recast material in the machine surface. Okay, right. So, however, debris impacts uh, reduce the material removal rate, but appropriate flushing arrangements and more turbulence and vibration effect will maintain the appropriate debris in the dielectric fluid medium so that uh, it enhances the removal rate and reduces the recast material in the machining surface. Right. Consequently, the structure modifications are minimized. Less micro cracks are observed, which increases the fatigue life of the machine parts if compared to normal EDM. Okay, so here EDMES will give the structure modifications which are very much required to reduce or minimize the micro cracks, which increases the fatigue life of the machine parts if compared to normal EDM process. So with this, I would like to conclude. These are the various references associated to this presentation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.